All right, if you're here for the mechanical noise webinar, you're in the right place. My name is Bill Holliday. I'm going to get started here in a minute. There we go. If other people join, there will be a rebroadcast, so I'm not going to delay. It's about 20 minutes. I'll talk about mechanical noise. Let me run through this. I think it actually says what I'm going to speak about. There we go. Bill Holliday, I'm a PE, I'm an acoustical consultant, and the goal is to understand heating, air conditioning, ventilation, but other mechanical issues as well. It's kind of a broad topic, mechanical noise. We deal with mechanical noise and vibration all the time with all types of projects. It could be environmental noise, could be industrial noise, where we're trying to deal with certain pieces of equipment, but I'll focus more on the air conditioning, ventilation in a building, that type of noise. We'll talk about noise sources, paths, mitigation measures, terminology I'll go through. So this is the outline of what we'll cover. Design criteria, configurations, radiated noise, fan, noise control, controlling the noise generated by the airflow, breakout noise, equipment vibration, just what you do once you've identified what the noise source is and that there is a problem that you want to solve. How do you address that path, that noise path, and then environmental noise a little bit at the end. So terminology, real briefly. If this is a system, and this could be a rooftop system, but if it's in a mechanical room, we have the noise path of the noise coming from the fan just down the duct and into the space, and that's duct-borne noise. There is noise that can be generated, flow noise at transitions, and that would be, airflow noise. You can get noise at the diffusers, airflow noise, or at abrupt transitions. Flow noise, not necessarily fan noise, but it's coming down the duct and radiating out the diffusers. There is breakout noise. Noise is breaking out of the duct into the space, and it'll be breaking out at this end too, but we don't care because it's within this space. We'd like it to break out here instead of out here. Noise radiating, case radiating from the unit, and if it's on the roof, that could be an environmental issue, but it can be an issue through the floor as well. Vibration would be another path. I don't see in this. Break in would be noise breaking in the duct and then going down the duct and either breaking out or going through the diffuser. There's also return air noise, and a lot of times they have these open plenums, and that can be a path of noise. The airflow is going to the unit, but the noise would be traveling the other direction. All right. Crosstalk is just a terminology, I guess. Noise from diffuser to diffuser. You could have it between offices, having nothing to do with the unit noise, but just the ductwork providing a path between spaces, and that could reduce speech privacy. Noise criteria, there's two basic tools they use, a noise criteria and a room criteria. Another one is, well, just the A-weighted noise level, but typically for HVAC noise, we're using this noise criteria, room criteria. Noise criteria, just have a series of curves. You look to see where your spectrum, so if you measure the noise in an office or in the area of concern, you plot the octave levels. Wherever the highest octave band touches, that's your NC curve. I mean, it's kind of related to A-weighted, but you could see the difference. If you had octave levels that follow this curve, the A-weighted level might be higher than if just one touched and everything else is real low. So it could vary somewhat from the A-weighted levels. Room criteria, similarly, you're going to get this. You're going to look for where the where am I? The rating system, single number, again, descriptor. And the room criteria has two parts to it. It's speech interference level, and then this other descriptor that's if it's neutral, rumbly, hissy, tonal, and perceptibly induced vibration. So again, you're plotting, you're going to, take an average and follow the curve, but then it's also, if you're above it in the high end, they call it hissy, so you put an H at the end. If you're above the range in the low end, they're going to call it rumbly, and if you're up in this area, they're going to give you a penalty. This is real low frequency. I guess that's another difference between the two. One starts at 63 hertz and one goes down, a lot lower, 16 hertz. Which is different than an A-weighted 2, which is going to give you these aren't perceived as much, but it is an issue with HVAC equipment, that low rumble from either vibration or from breakout noise, that low frequency. So configuration, mechanical room, equipment, where you put that room is key. You don't want it above a noise-sensitive space. We see equipment placed all the time, rooftop units above classrooms. And sure, you can mitigate it, but it just costs more. If it were over a hallway or some utility room or some room that's not as noise-sensitive, that makes life a lot easier. Fan unit selection, you want it to be operating efficiently. You can get noise issues when you're operating out of the range of the unit. How you set up the return system. If you need it to be quiet, you really should have it ducted. So a ducted return instead of just some open plenum. Open plenum is going to be less expensive. So for a lot of cases, that's fine. Rooftop air handling systems. There's just a lot of paths. Well, same with mechanical rooms, but you just got to be careful with radiated, as with the equipment room, going through the roof, going through the walls and floor ceiling, the duct borne and breakout noise. So ducts, be careful when you're breaking a barrier that you seal it well. You don't want duct work. You don't want gaps. Gaps really, noise works a lot like light and water. If there's any gaps, it really makes the wall a lot less efficient. So seal them up well, have as small holes as possible, but don't resiliently connect them where the pipe or ductwork is shaking the walls. So you want that to be a non-hardening, resilient seal. Unit location, you don't want it to be right next to abrupt transitions. The airflow, these are rated, the noise ratings that we're using as predictions are assuming even flow across the entire unit. So when you have these abrupt transitions, you are slamming a lot of air to one side sometimes, and it can cause uneven flow over the unit. You'll see these non-symmetric intakes and even discharges will just increase the noise. And if you disrupt the flow, you'll generate some low frequency noise, which could be an issue. Same thing on the intake. You want it to be even flow, so obstructions are not desired. Just keep the distance from any transitions or adjustments. All right, there's terminal units. A lot of times, I guess these in certain situations make sense. So what that would be is instead of just having one big unit or a bunch of little units pushing air through all the way to the diffusers, you could have a big unit and then have throughout the building have these VAVs or terminal units that will either will have a fan inside of them usually, or they'll control airflow, and they can radiate noise. You just want to be careful. Ideally, you keep the flow to them even, the flow out as even as possible. Isolation from building. Yeah, enclosing mechanical equipment room. Yeah, I mean, these are the issues we're going to deal with. Walls, floors, ceilings. If the fan noise is an issue, you can line the duct, which just means putting fiberglass, usually 1 inch thick, could be more or less, but depending on the frequencies you're trying to attenuate, the thicker attenuation, thicker material will help at lower frequencies. And for a certain length, you can put duct liner, and that does help a lot with higher frequencies, especially. The sound attenuators, those will help with low frequency. They're very thick amount of usually fiberglass with perforated metal to protect the fiberglass, and acoustically allowing the absorption to take place. Just be careful, you're constricting the flow. So there is tables of, given the amount of flow, what noise is generated by the silencers. So this would be a rectangular and a circular, but notice the flow is constricted quite a bit. And they can be sized, they need to be properly sized, but they're going to generate some noise. But if you're trying to attenuate low frequency noise, that's a great option, these silencers. Silencer placement's an issue. You don't want it right in front of a fan. I think I have a drawing here too. You don't want it way in the room you're concerned about, because there could be breakout noise before then. You don't want to way in the mechanical room or on the roof where noise could break in, or where it's attenuating before before it hits the wall, because noise can break in after the attenuation has already occurred. This isn't bad, but ideally you'd be straddling that wall. What else? Same thing with the flow. These silencers are going to constrict flow. You don't want to slam all of the air to one side or the other. You'd like the flow to be as even as possible. There are elbow silencer, all types of silencers, and you just want it to be as even as possible, so it's as effective as possible. So for airflow noise, you want to look at or be aware of the speed of the air. Discharge ductwork, transitions, diffusers, grills, anything that's going to generate some noise. You just want to be aware of it. Try to keep the flow as smooth as possible over those diffusers. So regenerated noise from flow, just keep the transitions as smooth as you can. So, this is a bad situation if you don't have enough length before the transition. I guess that was the point of this. Just keep those lengths so that the transitions aren't right in front of a fan. Same with these other type of transitions. A T transition, you're going to generate a lot of low frequency noise when you disturb the airflow. Keep them as smooth as you can, the transitions, and as symmetrical. There's recommended airflows for certain types of transitions. This is an option for those plenum returns where you just have an open grill in the ceiling. If you're trying to attenuate that path, you can put a boot on it, lined boot with fiberglass is one option. You can put even adding to the ceiling with chip and fiberglass to improve the transmission loss of the ceiling and that opening. Like I said, noise works a lot like air and water. So if you do beef up these ceiling tiles but leave an opening, it's not as helpful. You can even treat the light fixtures. So breakout noise, You can use circular duct, keeps the noise in, it doesn't let it break out, but just to be aware that that low frequency noise, if you keep it in the circular duct, you're pushing it down the system. So it's going to break out eventually, unless you attenuate it with the silencer, if there's some attenuation. But by just not allowing it to break out, you may be dealing with it at the diffusers or at the openings or further downstream. So a lot of time, I mean, sometimes it's fine to have it break out just over non-noise sensitive spaces underneath the unit or right next to the unit room, and then further downstream you'd be okay. But if it breaks, if it's right there at a noise sensitive space, circular duct's an option. Lagging, just boxing it in, or put in a silencer. So lagging, you're trying not to touch the ductwork if possible. Constructing an enclosure around it with fiberglass. We find with existing units, a lot of times you don't have this kind of space. So we'll use a mass-loaded vinyl with a fiberglass. It can be quilted right onto the unit, right onto the mass-loaded vinyl. But it's a heavy 1 pound per square foot or 2 pounds per square foot vinyl that can be Velcroed together and cut to fit. Yeah, but this would be a lagged gypsum enclosure. So equipment vibration, determine the amount of vibration, so when we're trying to figure out how much is from vibration for a rooftop unit or below an equipment room, a lot of times you can't just straightforward say, oh, or feel the ceiling and say, that must be vibration. Because low frequency noise can hit walls or partitions and shake them. So usually what we're doing is predicting the noise from the airborne paths, from the noise radiating from the unit or breakout noise. And then we're predicting how much noise we expect in that room below or adjacent. And a lot of times if it's not close to that, we suspect that vibration could be an issue. So we determine the amount from the airborne paths. We predict the amount from the airborne paths. If there's the measured levels are different or a lot higher, it could be structure-borne, could be the issue. We also do just predictions of structure-borne noise when there's a new build, something being built. We're looking at the stud or the structure, roof structure, spacing of the joists, looking at the stiffness of that roof system, looking at the construction of it to see what kind of vibration isolation is needed, what kind of units, and how much isolation is needed, and come up with a deflection of the vibration isolators and types that are needed. So you have different types of bases, equipment, isolation. You don't want any hard connections. You want to keep it as resiliently connected as possible. So any ducts, conduit, anything you want to have resiliently connected. So environmental noise, there's no single rule for how to deal with this. If you have rooftop or outdoor units, ground units, you have to just comply with the regulations. So each city, state, county, could have a regulation. Some don't. Some states don't have a regulation. Each city has their own. Some counties do, some don't. Some are very clear what the regulation is. It could be 50 decibels, 1 hour average, LEQ during the night, 55 during the day, or it could be, it just can't be audible inside a home, or it can't be a nuisance, or it can't be disturbing. So you're stuck with, look at the regulations, see how well defined they are, and then put in barriers, adjust equipment location, orientation, duct work for silencing, either intakes or exhausts if needed. There's a number of controls that can be done. A lot of times it comes down to barriers because you don't want to affect the airflow. and a barrier can be very effective, depending on how much noise reduction is required. We have had orientation be the difference. Just face a different direction, move it to a different part of the roof if possible. All right, that's about 20 minutes. I'm going to stop here. We're noise engineers, acoustical consultants. We're independent. We are full service. We can help with analysis. We can help with measurements, compliance. We can give expert testimony. We can write reports. We can provide you with materials that are needed, sound attenuating materials. We can connect to get installations done as well. So from predictions to measurements to materials to installation. We deal with all types of noise: environmental, sound isolation, room acoustics, mechanical, vibration, traffic, testing, product noise, expert testimony. Noise expert is a disadvantaged business, so for government projects that can be helpful. We are located in Phoenix, Arizona, Tucson, Arizona, San Diego, California, and in 2 locations in Mexico, Mexico City and Hermosillo, Sonora in the northern part. All right. Let me know if you have any questions. Email me. Well, you have my email here, noiseengineers.com, Bill, or go to the site. All right. Thank you.